Welcome, friends. Today, we are going to be learning a little bit about the layers of the Earth and the evidence that we have that makes us think that those layers actually exist. Okay, so step number one is please make sure you've read through the first two pages, page 210 and 211 of this Earth's Layers reading. Okay, now that you've read through those two, pause if you need to, go back, read them. For real, read them. Not joking. Okay, now you've read them. Good job. So basically the big takeaway there is we know like nothing about what's inside the Earth. I mean, now we have like some good ideas, but we can't actually see it because we're on the surface of the Earth. So we have to rely on evidence. So one of the evidence pieces that we are looking at is we're looking at where we happen to see earthquake waves. So here we have a little view of how earthquake waves work. All right. Boom. All right, so we're going to call this Earth's Layers Notes. I have this on page 36, but your page numbering system may be different. Feel free to make it whatever number actually works. And for the Earth's Layers Notes, oops, let's undo that. All right, so let's start by drawing a little image of the Earth in black here around the outside. And we know that there are a variety of layers in the Earth. We know that there is the crust that's represented by the black, and then there's the mantle, which is this section in the middle. And then we know that there's an inner core and an outer core, but we didn't know that all the time. So what we ended up finding was if an earthquake takes place, we would expect that those earthquake waves would follow these red lines. So the earthquake would take place right here, and we would see this kind of like earthquake. It's not actually an explosion that looks like a terrible explosion, but an earthquake's just a shift of the plates on the surface of the Earth. And we would expect that the earthquake waves would run along the surface, going that way. They'd probably run along the surface the other way, going this way. So we'd have surface waves. Then we'd also have some waves that go through the middle. So we'd see a wave going straight through here. And then we could pick it up on a seismometer or a machine that can read earthquake waves over on this part of the Earth. And then we'd have one that goes through the middle over here, and it would read on a seismometer out here. And then same deal anywhere else, right? So we could have waves here, we could have one going out here and have it picked up right there. So we could see at different seismometers, and it would show up because waves travel at a constant speed. It would show up at a linear time scale depending on how far away you are from the site of the earthquake. Turns out that's not actually what we saw though. What we actually saw was sometimes, well, first off, the surface waves did show up. So these ones along the surface, yep, that was accurate. We did see the waves traveling along the surface. We also saw some locations, like out here, we actually saw that point showing up. Same deal here and here and here. But then there were some locations where we saw this kind of like dead zone. And that dead zone would be like from here-ish all the way around to here-ish, where we just didn't see any earthquake waves showing up. And instead, what we saw was that the waves would come down and then they would show back up again a little bit later on the surface. So down and then bouncing back up, or down this way and then bouncing over here, or sometimes they'd even get kind of like deflected and show up over here. So it'd kind of do like a little sideways bounce. And what that told us was that there has to be something out here in the middle that's getting in the way. And we figured whatever it is, we're going to call it the core, right? It's something in the center. And so we decided there must be a core there. And then we did some additional experimentation and decided, hey, there's probably actually something more than just a single core. There's a solid core and a liquid core. And then based off of different things that we're able to go through and not, so different waves that could travel through. All right. So then we also know that there's this MOHO discontinuity, and that's between the crust and the mantle, and that was explained in the reading. All right. Another thing that was in your reading is the magnitude scale of earthquakes. So the magnitude scale of earthquakes is also sometimes called the Richter scale. But every time you go up by an integer, so for example, 5 to 6 or 6 to 7, the earthquake gets 50 times more force and power. So a 6 is 50 times more intense than a 5. A 7 is 2,500 times more intense than a 5 because 50 to 6 times 50 to 7, they multiply together. 50 times 50 is 2,500. All right. There are other factors that lead to damage in earthquakes, and those are things like depth, location or proximity to cities, the quality of buildings, the ground surface. For example, a few years ago, we had a couple earthquakes that took place really close to the same time. One was in Chile and one was in Haiti. And you're probably more familiar with the Haiti earthquake because that's the one that did a ton of damage. But it turns out, like in the same week, there was a larger earthquake that took place in Chile. But the Chilean earthquake was deeper under the earth, which means it was further away from the surface and thus going to do less damage. It was near a big city, but that big city was really, really well engineered and built. Whereas in Haiti, it was very soft soil, and the quality of building, because Haiti is a much lower income country, was way, way less. So in Haiti, they had lots of like concrete block buildings, and those concrete blocks, once they started shaking, cracked and crumbled and were just completely destroyed. So many, many people's homes were destroyed. Many, many people suffered severe injuries and died because parts of their homes fell on them. And that was because they weren't very well engineered. Now, the good news is we live in California, and California is a relatively high income place. We have lots of resources, and our buildings are really well engineered. Like, if anybody's going to build well engineered earthquake buildings, it is California and the Bay Area. So it's likely that our buildings are really well engineered, and so we're not going to be in a tremendous amount of danger. Obviously, if an earthquake happens, there's going to be some damage, but not severe, severe damage. Now, we do, however, have the problem of being located right on a fault. We have the San Andreas Fault that runs right along our coast. So out by Point Reyes, the San Andreas Fault runs right through the middle of Tomales Bay and then right outside the Golden Gate Bridge. So it just runs kind of along the coast of Marin County. And then there's the Hayward Fault that runs through UC Berkeley and the East Bay and kind of travels along the hills of the East Bay there. So we have two faults on either side of us that are both reasonably significant and could lead to some good shaking. All right. So now we also know so far that we know very little about Earth's interior. We know that it's hot. We know that there's some water there. We know that earthquake waves show us what might be present. So that's about what we know, but most of what we know is not much. We can look at the evidence, and the evidence right now is earthquake waves and a little bit of digging that we've done. And then we can make our best guesses based on that. Okay, so you are now ready to continue your reading. But before you do that, I wanted to show you a couple of pieces. So I wanted to show you a few little examples of some diagrams. So we've talked a little bit about the earthquake waves, and I wanted to show you what a seismograph would actually look like. So here's what a seismograph looks like. You can see that there's little zigzags as the earthquake has come. It's shaken the roll of paper, or we now do it digitally, but it's shaken it up and down, and that's put these little zigzags into the seismograph. The S wave, or sorry, the P wave is the first one to arrive. And so you'll see the P wave is getting there right around 5 seconds, and that has smaller shaking. The S wave is the second one to arrive. P stands for primary, so it's first. S stands for secondary, meaning it gets there second. And the S wave has larger shaking. So the zigzags get bigger in magnitude because there's more shaking. And then finally, you have these big shaking ones. Those would be your Rayleigh and your Love waves, which are the surface waves. And that's what does most of the damage, is these very large ones that show up about halfway through the seismograph. So P waves and S waves can travel through the middle of the Earth. And then let's take a look at what that actually looks like. So I tried to draw a little version of this, but here we have the earthquake starting on the surface over on this side. The P wave and the S wave can both travel through the mantle, no problems there. The P wave can go through here, but it can't travel through the liquid, or if it does, it ends up getting bent. And we're going to talk about this more when we get to waves, because waves bend as they transfer from liquids to solids or between any two media. As they transfer between mediums, we see a bending of waves. So we have this little P shadow where we don't see any P waves in that zone. And then we have this really big S wave shadow because S waves can't travel through liquids at all. So the S waves can get to there, they can get to there, but they can't get anywhere through the core. So there's this big zone on the other side of the Earth where we're not seeing any S waves. The P waves, you get some P waves straight through the middle, but they've been deflected a couple times. And so then there's certain areas that you don't see P waves because of the deflection patterns. Like I would go up here and then I'd get deflected and I'd end up out here. So there's this little zone where all the waves would get deflected away. Cool. So if we take all that information and we pay attention to how waves have been deflected, we can actually make a pretty decent map of how thick the crust is in different locations. You'll notice blue here is very, very thin crust. Green is kind of medium sized. And then the darker it is, and like the reds and the browns, the thicker the crust is. So we have a lot of areas of really, really thick crust, and those really thick crust places tend to be where there's really big mountain ranges. So right here, this is the Himalayan mountains, where there's the 70 in the middle of Asia. And that's because you have two continental plates that have bumped up against each other. One's gone underneath the other one, causing it to kind of like rise up. So that's the Indian plate and the Asian plate crashing into each other. And that leads to a big mountain range. That's where Mount Everest is and most of the largest mountains in the world. And it also leads to really thick crust because you've got the crust underneath plus the crust on top. So that's a lot of crust before you get to the mantle. Same deal here. This is the Andes Mountains on the coast of South America, the west coast of South America. That would be like Peru, things like that. And you can see, again, we have some really dark, thick crust there. And that's because the oceanic plate is subducting underneath the South American plate and causing that big mountain range as it kind of crumples up on top of itself. And then you'll notice that the thin crust is in the oceans. That's because that crust is being formed from the plate boundaries. So divergent plate boundaries lead to new crust, and oceanic crust is quite a bit thinner than land crust, continental crust. All right. Other kind of neat stuff. Now we have some information. So here, actually, we don't have this information yet, but you soon will. So very shortly, you're going to start reading again. In fact, you can almost do that right now. So as you start to read again, you're going to start from page 214, where it says start here. Go ahead and read through. When you get to page 216, there's a little footnote. In that footnote, I'm going to take that information and make it into a diagram. So this has information about how large the different layers are. If we take a look at that, it gives us a setup kind of like this, where we've got the inner core, the outer core, the mantle, and then the crust. The crust itself is really, really thin, between 10 and 75 kilometers for continental crust and only 5 kilometers for oceanic crust. And that compares to 2,900 kilometers for the mantle, 2,200 kilometers for the ocean core, like 1,200 kilometers for the inner core. Maybe it's 900. I can't see the number there. And we've also got the Moho discontinuity and the Gutenberg discontinuity between the mantle and the core. Here's a different view of it with chemical composition. And then finally, at the very end, we'll see what causes all of this motion. And all of this motion is caused by the process of circulation. And that circulation is through convection currents. So there's a lot of heat stored in the core that heats the mantle. The mantle rises and does this very slow motion, but it's moving like at the speed of glass falling down your windows. So you can't see it. It's going really, really slowly. So the mantle is like a solid that's pseudo liquid. It moves really slowly, but fast enough to cause plate tectonics and plate motion. So I've linked this on here so you can crank through and take a look at all these various images. Kind of fun. All right. Last piece is once you get to 216, I'm just going to record the video part of this now as well. Let's talk about the layers of the Earth. Okay, so layers of the Earth. Going back to our notes and writing some stuff down again. There we are. All right, so now let's talk about the layers of the Earth. Layers of the Earth, and I've done this in miles instead of kilometers, but in terms of depth, this is a very rough sketch of what's going on. The crust on the outside has a thickness of about 25 miles. I haven't drawn a separate layer for the crust because 25 miles in our scale would be like less than the thickness of my pen. So that black line, that is the thickness of the crust, or even less than that, right? I maybe should have had a thinner pen in order to make it proportionally 25 miles. Then you've got the mantle that's 1,700 miles deep. The entire radius of the Earth is 3,960 miles, close to 4,000 miles. We can roughly ballpark it at 4,000 miles, but it's a little bit less than 4,000 miles in radius. So that's an 8,000 mile diameter or a 7,920 mile diameter approximately. The outer core starts at 1,700 miles and goes down to 3,200 miles. So that would be like from here out to there. And if you subtract those two, you can see that you've got an outer core of about 1,500 miles. And then finally, the last 700 miles or so are inner core. And that inner core is solid iron. And we think that that outer core, that liquid outer core, is what gives our Earth its magnetic field. And we assume that's due to spinning of the liquid core. Again, we haven't been down there. It's not like we can see the liquid core spinning. We are looking at the evidence, which is that we have a magnetic field around the Earth, and assuming there must be some liquid iron that's really, really hot in order for it to maintain its liquid nature, that could provide that magnetic field by doing some rotating. And when we talk about electricity and magnetism, this will hopefully make a little bit more sense because we'll talk about how moving of a current can lead to a magnetic field. All right, so that heat leads to this convection current out here. And these would be going on all around in the mantle. So all over the place here. I could draw another one where it's heating up down low. That causes it to rise because warm things rise. Then it moves along the surface and it cools down. And then once it's cooler, it sinks back down again. So that's a convection current, and that's what causes the plates on the surface to do some moving. All right, so go ahead, head back to your reading. On your reading, whoops, where are we? Am I here? There I am. So on your reading, read all the way through the end of the article. Make sure you've written down all of those notes, and then watch the 2 videos that give you like an analogy or an example of how convection currents might work. All right, so that is what we know about the layers of the Earth and the evidence that we've used to create that model of what we think is happening inside the Earth. Enjoy.